Okay, so in this video we're going to talk about kinetic molecular theory and real gases, which are from chapters 11, sections 7 to 8. So far, when we've talked about gases, we've been looking at an experimental point of view. So pressure being less than 1 atmosphere, and most of these gases are approaching the ideal gas. What we have to remember from the scientific method is laws are generalizations of many observations, and they will help us to predict behavior, but they do not explain why. The answer as to why it happens is constructed from theories and models. If you recall, models consist of speculations about what individual atoms or molecules might be doing to cause that observed behavior. So for a model to be successful, it has to explain observed behavior in question and predict correctly results of future experiments. You also want to remember that theories are never absolute, and you want to try to avoid using the word proven with them, but they often provide defined boundaries for what we're looking at. And it's a good approximation of what's going on. But every now and then you'll see some failure of them. So what we're going to go into now, because we've talked about all these gas laws, now we're going to look at kinetic theory as to what's going on. And so this is going to be the explanation of the properties that we see with ideal gases, and the behaviors that are coming from them. And then we're going to look at how real gases actually behave. Okay, so a few postulates of kinetic theory of gases. First is that a gas consists of an extremely large number of very tiny particles that are in constant random motion. The next is gas particles themselves occupy a net volume so small in relation to the volume of their container that their contribution to the total volume can be ignored. What this means is that gas particles are just kind of like a dot in the total volume. They're not taking up any space, really. And then the last postulate is the particles often collide in perfectly elastic collisions with themselves and with the walls of the container. Perfectly elastic collisions, again, those are the collisions where the force of the contact is the same force of release. So if you were to drop a ball from a certain height and it bounces off the ground, if it goes right back to where you dropped it from, then that would be a perfectly elastic collision. It didn't lose any of its energy. These gas particles will move in a straight line between collisions, and they don't attract or repel each other. So these are the three things that we always want to keep in mind with kinetic theory of gases. And another important idea with kinetic theory of gases is that we have to remember that kinetic energy is the energy involved in movement. So if you drop a pen, the energy of it dropping is kinetic energy. And then temperature is proportional to the average kinetic energy. So if we increase temperature, then we increase the average kinetic energy of gas molecules. You want to remember that real gases don't always follow these postulates, but the kinetic theory does explain ideal gas behavior, and its predictions fit experimental observations. So let's look at the kinetic theory and the different laws. So first, if we look at Boyle's law, what we see is, so what we have here is a container with a piston that can change height. And so if we have the same number of molecules in each one, what happens is as we increase the pressure, it's decreased the volume. As we decrease the volume, we increase the pressure because they're going to be colliding more often with the walls of the container compared to one with greater volume. So you can see how this kinetic theory is fitting with Boyle's law. Next is kinetic theory and Gay-Lussac's law. So we have mercury barometer, or manometer. where we see gases in this container, and we can measure the change in pressure based off of how the U-shaped curve changes. So, if we increase, so we have these gases in a container, and we heat it, what's going to happen is they're going to collide more and push down on this, causing an increase in pressure. Next is Charles' law. So if we have a reservoir for the mercury to go into, and we heat the gas particles, what's going to happen is we're going to have a change in the level of mercury in here, because these are now taking up more volume, because of that higher energy and greater amount of collisions. With Dalton's law, it can be actually seen as evidence of kinetic theory. The only way Dalton's law can be valid is if each particle acts individually or independently of each other. Graham's law, where I'm actually going to go through the derivation of it all for you now. So, what we see is if we have two gases of the same kinetic energy, so we have Ke of 1 is going to be equal to Ke of 2. The equation for kinetic energy is it's half of the mass times the velocity squared, or the average velocity squared. So if we're looking at if the kinetic energies are equal, then half the mass of 1 times the velocity of 1 squared is equal to half the mass of the second particle times the second velocity squared. We can eliminate the 1/2 and rearrange and find that the velocity squared of the first particles divided by the velocity of the second particle squared is equal to mass 1 over mass 2. Or V1 over V2, the velocity 1 divided by velocity 2, is equal to the square root of mass 1 over mass 2. And since the mass is proportional to the molar mass, what we find then is V1, velocity 1 over velocity 2 is equal to the square root of mass 1 over mass 2, which equals the square root then of the molar mass of 1 over the molar mass of 2. And the rate of effusion is proportional to the velocity, and that's what gives us our equation of the rate of 2 over the rate 1 is equal to the square root of m1 over m2. So you can see, because the kinetic energies are equal, the rates of effusion, the ratio of the rate of effusion to the square root of the ratio of the rates of masses are going to be the same. Okay. Lastly, let's look at what absolute zero is again. So, because temperature is proportional to the average kinetic energy, which is proportional to 1/2 the mass times the velocity squared. So kinetic energy then, if we bring it to 0, then the temperature will be 0. The only way for kinetic energy to be 0 is if the volume is 0, since the mass cannot equal 0. So when gas molecules stop moving, then a gas is as cold as it can get, and that's when we have achieved absolute zero. You should recall what absolute zero was from last year's chemistry class. Okay, so let's look at some deviations from ideal gases. First is that gas molecules have finite volumes. What this means is that they're actually taking up space, and so there's less space of the kinetic motions. What this means is that the particles are hitting the walls of the container more often, and so the pressure is higher than expected compared to ideal. So what we see here is if PV over T if we're looking at those ratios. If it's 1, as we would see with an ideal gas, then we see that no matter how we change the pressure, that ratio is going to stay the same. What we actually see is at different pressures in atmosphere, we're going to see a deviation from ideal. You can see at 1, right, because we're going from 0 to 200 on this line. At 1 atmosphere, oxygen gas is behaving pretty ideal. But as we increase pressure, it's going to deviate from that ideal gas. Another deviation from ideal gases is that the particles actually do attract each other. They have very weak attractions, but it's going to affect how often they hit the walls of the container. And so that can make the pressure less than that of an ideal gas. So you can see, right, the attraction between them is going to cause them to bend, repulsion, push away, versus neither. So, right, so if they're pulling in towards each other, they're going to collide instead of colliding with the wall. They're going to hit different parts of the wall here, versus here they're just going to hit them together. So it changes the amount of collisions occurring. You can also see the differences in how we view ideal versus real gases in terms of their attractions to each other and how that's going to change their path, right? In ideal gas, we say that the gases are just moving in a straight line. There's no attraction or repulsion with each other. But in real gases, they're going to curve around each other and change their direction. And we can actually predict these changes using the van der Waals equation for real gases. You shouldn't have to actually use this equation. I just want you to know it and understand it. So it changes a few things. You can see that first we have to correct for pressure, and then we correct for volume. And so we have these two pieces that change it. A and B are van der Waals constants, and they change depending on the compound that you have. We find them from measuring pressure, volume, and temperature for the real gases over a wide range of conditions, and then we can calculate it based on these equations. You'd actually probably plug it into some sort of like supercomputer and find the actual constants. So some things that we know. So A is correcting for pressure. And so it indicates some attractions between the molecules. A large A means that there's strong attractive forces between molecules, and a small a means that it's a weak attractive forces between molecules. Because that means then it's not actually going to change that pressure very much if it's small. B is a volume correction. And this deals with the sizes of molecules. So a large B means that we have large molecules, meaning that they're taking up more space. And a small b means that they're smaller molecules, so they're taking up less space, so they're not changing the volume as drastically. We know that gases that are more easily liquefied tend to have the largest van der Waals constants, right? Because if they're easily liquefied, then they're easily brought together. All right. So that is it on the kinetic theory and the variations in real gases.